Assalamualaikum class. So today we're going to discuss on cell potential and how we can actually arrange our two cell potential into a redox equation. Okay, so given here, the cell potential is a voltage of an electrochemical cell. Okay, so we have two electrode and then we know the electron is moving from anode to cathode, and they produce a voltage, some voltage. So A cell of a voltage cell depends on the difference in electrical potential between the two electrodes. So the bigger the gap between the two electrodes, therefore the bigger or the more voltage can be produced. Okay, so refer to the standard electrode potential list for a value. So here is our standard electrode potential in aqueous solution at 25 degrees C. Okay, so if you notice here, the condition is all standard, yeah. So we have at 25 degrees C. Okay, it's supposed to be at 1 atm and the solution is at 1 molar. Okay, so if you look here, we have standard potential ranging from -3 up to positive 2.87. Okay, so there are so many. Okay, there are so many half reaction here. So how can we use this half reaction to produce a common redox reaction that we always use? Okay, so having that information, okay, so we refer to that data, we actually can set our mind on these two major things first. Firstly, the more negative E cell value, okay, E naught cell value, the easier for it to donate electron. The more positive the E naught cell, the easier for it to accept electron. Okay, so look here. So we have lithium -3, meaning that lithium is very prone to giving out electron. As we can remember, okay, if we look at our periodic table, lithium is group 1. Okay, group 1 prone to give out electron in order to achieve its octet. Whilst, if you can see here, the lowest down here, fluorine. Fluorine, on the other hand, very willing to accept electron. Because why? There's only they need only one more to complete the octet. Okay, therefore, fluorine here, okay, fluorine plus 2 electron producing 2 fluoride ion. Here is the most easy, okay, the easiest atom to receive electron. Okay, so most likely it become cathode. Okay, so receive electron, cathode. Donating electron out here is anode. Okay, so what's the point here? The point here, if you have two electrode. So let's say first one you have calcium. Okay, first one you have calcium, and second one, let's say we have iodine. Okay, so if you have these two half reaction, how are we going to determine which one is anode, which one is cathode? Okay, so first thing first, you get to this table and then get their value. So value here is -27 and this one is 0.59. So 0.59 is more positive than -2. Therefore, iodine is easier to accept electron, meaning that iodine will be at cathode and calcium will be at anode. Okay, so that's the basis of it. Alright, so when we know who is easy to donate and accept electron, therefore we're going to look at the example using half equation to write down a redox equation. So as we discussed in our previous class, okay, so by now you need to know how to write down your full redox equation. Is it important? In a way, yes. Okay, because we need to know how many electrons there are in our redox equation. Why? Because we're going to use that number of electron in our next subtopic. So now we're going to learn how to write a redox equation by using two half equation. So this two half equation, if you look here, tin plus 2 electron producing tin solid, and silver plus electron producing silver solid. These both are reduction equation. How do I know that? Because we add electron, meaning that the ion receive the electron. So when they receive the electron, meaning that there are reduction process. Okay, so you can find here, kat sini, we have here tin. Okay, we have here tin and also our silver. Okay. Alright. So let's say we don't have our table there. Okay. Let's say we don't have our table, only given this information. So we need to know here. The first thing first we need to know is we need to know who is anode, who is cathode. In other words, we need to identify which one going to be anode, which one going to be cathode. So as our previous slide, okay, the more positive will be cathode, the more negative will be anode. Okay, so the more positive anode will be at cathode. So we compare these two equation. So this one is negative 14, negative 0.14, and the other one is positive 0.8. Therefore, tin is anode, and silver is cathode. Okay, so then we write down the reduction half equation. So kita siapa yang who's going to undergo reduction? So we know that silver will undergo reduction. So we write down as it is silver plus electron producing silver solid. Okay, so the E naught of Eg equals to 0.8 voltage. Okay, so we done to step 2. Now we look at step 3. Write down oxidation half equation. So now we know that tin is undergo reduction, but the equation shows other way around. So what we need to do, we need to adjust the equation. So if you notice both equation given in reduction equation, therefore what we need to do is first we need to reverse the equation. Okay, so it says here reverse the chemical equation. However, the value and sign for E naught remain, meaning that we only reverse the equation, meaning we write down here tin, okay, tin solid producing tin ion plus 2 electron, producing E naught tin, which is negative 0.14. So like I said, please take note that you don't have to change sign for half cell, and you don't need to do anything to the value. Okay. And then step number 4. Balance the number of electron of these two equations. Okay, take note again. We multiply the whole equation, but we leave the E naught as it is. Okay, so in order to balance the electron, we have here, because tin here is 2E, okay, 2 electron. So for the silver, okay, we need to times by 2 so that we have 2 electron on both equation. So we need to multiply 2 for silver. So when we multiply 2 for silver, okay, silver, this one, kita multiply by 2. So when we multiply by 2, we going to get 2 silver plus 2 electron producing 2 silver solid. Do we change anything at the E naught? No, we will not change anything. That E naught remain as it is. Okay, so we have two equation now. One is oxidation and another one is reduction. Okay, so we go for the 5th step. Add the two equations together, cancelling the common species. So now, since we have 2 electron on the both sides, we can cancel them out. Okay, so we have here tin plus 2 Eg producing tin aqueous plus 2 silver solid. And what is the E naught cell? So for this 2 cell, we can calculate it by using normal equation. E naught cell equals to E naught cathode minus E naught anode. Okay, so 0.08 minus 0.14, then we get 0.94 voltage. Easy, right? So I really would like you to remember that when we reverse the equation in electrochem, it is slightly different when we reverse equation in thermochemistry or in chemical equilibria. So I really want you to take note that when you reverse an equation, when in thermochemistry, delta H sign will change. Okay, so when we reverse from positive, delta H will change to negative. Okay, positive akan tukar pada negative. Fine. Then in chemical equilibrium, what happened when we reverse the equation? Our Ka atau our Qc or our Kc, the value will go invert and 1 over something. Okay, so that is in chemical equilibrium. But now in electrochem, when we reverse the equation, our E naught cell remain as it is. Okay, so they just chillax. Do we need to change the sign? No, we don't have to change the sign. If we multiply the value, do we need to multiply the E naught? No, you don't have to touch the E naught. Okay, so every calculation is falls under E naught. Okay, E naught equals to E cathode minus E anode. That's all. Okay, so I hope by now, if given the two equation, you can write down your own redox equation.